Today we want to discuss something called significant figures. First of all, let's enter some numbers in our calculator. If we were in a math class and we had 8 divided by 3, we would put that into our calculator and we would get 2.666,666,667. We would have 9 digits. But what the calculator is assuming is not that we wanted to divide 8 by 3, but that we wanted to divide 8.0000000 by 3.0000000. And that's why it gives us this number with all of these digits at the end. But in physics or in chemistry, if we divide 8 by 3, we need to know what we really mean. Do we really mean that it has this many digits of accuracy, or did we simply take 8 things that were just maybe accurate to a tenth or to a hundredth? We need to understand how to show an answer, because this is the answer to this problem. But in a chemistry or physics problem, we are looking at maybe something we measure to 1 decimal place, divided by something we measure maybe to 2 decimal places. And certainly we need to know what the answer is, and it is not that answer. So let's go to the next slide and see how to do this. First of all, when we count figures or significant figures, we need to know that non-zero digits are always significant. So anything 1, 2, 3, 4, 5, 6, 7, 8, 9, those are always significant. The only ones we have to worry about, or the only one we have to worry about, is the 0. And it's a little more difficult to count. So if you have a number like 0005, the leading zeros to the left of the decimal place are never significant. So that's rule 1. Rule 2 is captive zeros, 60603. These are captive. They're captured in between significant figures. 1, 2, 3, 4, 5, 6, 7, 8, 9. Captive zeros are always significant. And finally, trailing zeros are significant only when they appear on the right side of the decimal place, 6.83000. These 3 are all significant. So let's go back over the rule again and see if we can get an idea of how to understand it. If we're talking about a number that has 0.003, how many significant figures does it have? Leading zeros are never significant, so this number has only 1 significant figure. So that's rule number 1. Leading zeros are never significant. How about this number, 0.30405? It has 1, 2, 3, 4, 5 significant figures, because all of the captive zeros count, but the leading zero does not count. So all the captive ones count, the leading one doesn't count. So how about this number, 0.3040500? How many significant figures does it have? This one does not count. All of these do count, because these 2 are captive and these 2 are trailing. Now let's talk about some specific things. If you have a number like 100, does that have 1 significant figure or 3? As it's written, it has only 1 significant figure because the trailing zeros do not count. Therefore, when we write out a problem, we try to do it carefully and put a decimal point here if we really mean for all of those to count. So if I put the decimal place here, then 100 has 3 significant figures, because these are no longer leading zeros. They're captured between this figure and the decimal place. This number, on the other hand, still has only 1 significant figure, because these leading zeros do not count. So that may be a little bit confusing, but when it's on the left-hand side, we have to put the decimal place to count the zeros. So let's Go and practice some more at the next slide. Here we have some problems to solve. How many significant figures does this have? The leading zeros don't count, so that has 2 significant figures. How many does the second one have? The leading zero does not count, but the captive zero does, so this has 4 significant figures. How about the next one? I'll let you do it. It has 4 significant figures because the captive zero does count. How many does this one have? It has 6 because this trailing zero does count. 1, 2, 3, 4, 5, 6. And of course all the non-zero digits always count. Now, how about the last one? How many significant figures does this have? The answer is 3. 1, 2, 3, the leading zeros do not count. I think this is much easier to see if you write this in scientific notation. That's 6.23 times 10 to the 1, 2, 3, 4, 5, 6, 10 to the minus 6. And now we see the 3 significant figures here just like we pointed out. So let's see if we can do something a little more complicated, or maybe just try a few more. Let's put a couple of other numbers down and see what we come up with. How about 1.50300? How many significant figures does that have? It has 1, 2, 3, 4, 5, 6 significant figures because these at the end do count. How about 1.006? How many significant figures? It has 4. 1, 2, 3, 4 because the captive zeros count. How about this number? 0.00600. How many significant figures? 3. Because the trailing zeros do not count, but these on the end do. Now let's go to the next slide. Now that we know how to recognize significant figures, let's talk about how to use them in a problem. When we work a problem, there are 4 things we generally think about doing. We can add, or we can subtract, or we can multiply, or we can divide. What we want to understand is when we divide numbers or add them or subtract them, how do we take our counting of significant figures and get a final answer? So if you had a physics problem and you measured something to 8.03 meters and you timed that to be 6.3 seconds and put this into your calculator, you would get 8.03 divided by 6.3. And you would have a number of 1.274603175. But if you put this down as the answer and turn it in, then I will clearly count off for this. This is not the correct answer because here is our rule number 1. If you are multiplying or dividing, the number of significant figures in the answer is the same as the number of significant figures in the least precise measurement. So, the measurement in meters has 3 significant figures. The measurement of time has 2 significant figures. So our answer can only have 2 significant figures. So our answer is 1.3, where we've rounded off to rounded the 2 off to a 3. So this is not the correct answer. This is the correct answer, and of course it has units of meters per second. So let's talk about this a little bit more, maybe work some other examples. Suppose let's just keep meters in seconds, so it can be any units, but let's just see what we have. Suppose we measured something to be 7.354 meters. And we had a really good stopwatch, and we calculated that we traveled 7.354 meters in 2.46 seconds. How many significant figures are in the numerator? 4. How many significant figures are in the denominator? 3. So when we divide this out and put this in for our homework or on a test, put this into our calculator, 7.354 divided by 2.46, we get 2.989430894. And if we put this on our test or our homework as our answer, then we will definitely get counted off. Because the correct answer must have what? The same number of significant figures as the least number in the calculation. So we will see that the correct answer is 2.99. 3 significant figures where I've rounded off the third one to be 2.99, and of course this has meters per second. So let's try one a little bit harder. Suppose we measure something and have 7.3500 meters, a very accurate measurement, and in terms of seconds, it's 0.036 seconds. Now, how do we show our answer? First of all, let's see what we get. If we divide that, we get 7.35. We get 204.1666667 meters per second. Are we going to put this down as our answer and put a box around it? No, because that's going to be wrong. The final answer can have only as many significant figures as we had in our multiplication division. So how many significant figures do we have in the numerator? 5. Because the trailing zeros count. How many significant figures do we have in the denominator? 2. Because these trailing zeros or leading zeros do not count. So how many significant figures do we have in our answer? 2. So our answer is going to be 20, and we can't count the 4, so it has to be 200. Now you say, well, how do I know that has 3 significant figures? You're going to have to write this in scientific notation as 2.0 times 10 squared. And that will show you that you have 2 significant figures because you've put 2.0 and the trailing zero counts here. Now we'll go to the next slide. Now suppose we are doing addition and subtraction, and we have 16.34 plus 7.2 plus 8.156. If we add those together on our calculator, we get 16.34 plus 7.2 plus 8.156, and we come up with 31.696. But this is not correct, because rule number 2 is for addition and subtraction, and it's different from rule number 1. Rule number 2 says that when you're adding and subtracting, the answer must have the same number of decimal places, not significant figures, but decimal places as the least. So our answer is not 31.696, but 31.7. It has 1 decimal place, just like the least significant number in our addition and subtraction. So the answer is 31.7. Suppose I had 17.43, 8.0169, and 2.0. I add these up and get that number. That is not the number we should write down. We look at the one with the least number of decimal places because we're adding these. The least number of decimal places is 1, so our answer is 27.4. Now, some special things. Exact numbers like pi or 3 apples have an infinite number of significant figures. 6 rocks, 18 computers, those are written as if they had an infinite number of decimal places. Infinite number of significant figures because they are an exact number. We have 3 apples, and pi is known to any number of decimal places we need. Some other things, there are by definition 2.54 centimeters in an inch, so we can treat that as if it's 2.5400000 and just keeps going. By definition, 1 cubic centimeter is exactly equal to 1 milliliter. So we could write that 1.000. When we use this in a calculation, this does not affect our significant figures, nor does this, because those are to infinite precision. Now for some practice. How many significant figures in each of the following? 3. They are all non-zero. They all count. How many in this one? 5 significant figures. 1, 2, 3, 4, 5. All the captive zeros, the 2 count. How many significant figures in this? We have 9.800 times 104. So we take 9.8 times 104, and we get a number like this, 1019.2. But how many significant figures should the answer have? 3. Only as many as the least. This one has 5 significant figures, so our answer here can only have 3 significant figures. So this is not the answer. The answer is 1.02 times 10 cubed, showing 3 significant figures. How many significant figures in 22 meter sticks? That's infinite, exactly 22. How many significant figures in this number? Leading zeros don't count. Captive zero does count. Trailing zero does count. So it has 4 significant figures. And how about this one? It has only 2 significant figures, because if we wanted it to have 5, we would have to put a decimal place here. Therefore, significant figures. First of all, you determine how many significant figures are in your answer. If the answer involves addition and subtraction and multiplication and division, you solve the addition and subtraction first and figure out the decimal places and significant figures for it. And then you follow the rule for multiplication. When you're calculating, carry 1 more digit than you will get in your final answer, and only round when you get to the final answer. Or if you put them all in your calculator, don't round at all until you get to the final answer. Now let's practice on these numbers. Write down the correct answer for the first one. When I multiply these on my calculator, I get 6.384. Is that the number I should turn in? Should I put a box around that number and say that's the correct answer? No, let's look at our rule. This is multiplication and division. That has 3 significant figures. This has 2, so how many should our answer have? 2. The correct answer is 6.4. I must round off the 3 to 4. How about the next one, which is an addition? On my calculator, I get 31.123. Is that the answer I should turn in? The rule for addition and subtraction says that you use the number of decimal places of the least one. So therefore my correct answer is 31.1. Remember, addition and subtraction uses decimal places, multiplication and division uses significant figures. Now how about the third one? On my calculator, I get 1.48695652. Is that the answer I turn in? No. The numerator has 3 significant figures. The denominator has 3 significant figures. They're both the same, so the answer has 3 significant figures, and the correct answer is 1.49, where I need to round that off. That is the correct answer. That one is not. Now we come to the most difficult one in the whole set. It has addition on top and division on bottom. So follow our rules and solve the addition first. I add 1.04 plus 3.2 plus 12, and I get for the numerator 16.24. But I follow the rule of addition. This number has no decimal places, so that means that I have to put the top answer as 16. Then I take 16 divided by 234.345, and I get 0.068275, and it goes on. But there are only 2 significant figures on top, so I must have only 2 significant figures in my answer. So the answer is 0.068. This is the correct answer, not this. 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 Now, your turn to practice. Let's specify how many significant figures are in each one of these. First one has 4. The next one has 3. What about this one? All 8 of those are significant. What about this one? It has 2.